Howdy, everyone. My name is Brittany Tarrin, and I am the chair of the SPE Permian Basin Data Analytics Study Group. The mission of this group is to build a community of data enthusiasts in the area by conducting knowledge sharing events such as this. Thank you for being a part of that community. Thank you for being patient with us during this time, and thank you for joining us for our kickoff meeting. We are currently working on our website, but please follow us on LinkedIn to keep up with further events. I am pleased to announce that our platinum sponsor, Petro.ai, will be presenting today. Please hold all questions until the Q&A session towards the end and use the raise hand feature in GoToWebinar. And now I will be turning it over to Jared Richardson with Petro.ai, who will give you more information on who they are and what they do.
Hey, Brittany, thank you very much for the introduction. And hello all, thank you for the opportunity to present here with you today. We're very excited to be a part of this first data analytics kickoff event, and we look forward to many more of these for the year to come. So my name is Jared Richardson, and I'm a Permian director here for Petro.ai. So I focus strictly on the Permian Basin, and really helping our customers in this area capture the value of modern analytics software for their organization. I'm also joined by Kyle LaMotta, our VP of Analytics, who's going to give a brief overview and a discussion on the impact of well orientation. Before we get started, I wanted to briefly share who we are and what we're focused on here at the company. So for Petro.ai, we're a leading data science company providing cutting-edge data science workflows for oil and gas. And what's unique about Petro.ai is that we have a deep bench of oil and gas veterans who really understand the challenges of oil and gas and the challenges that you all face today in the industry. We couple that with a data science expertise from Rice and McGill. And with that, we've built a very robust data platform that brings together the data, the people, and the analytics together all in one space. Now, while many are focused on the promise of digital transformation and the promise of analytics, in talking with dozens of operators, we have found that this digital transformation has really been stifled by what we call analytics friction. And what do I mean by analytics friction? Well, for many, we talk to the data that these engineers are trying to work with is scattered across their organization in many different silos and legacy applications. And it's also very rigid and hard to work with. And with that, we find that 80% of an engineer's time is typically spent on gathering data, normalizing data, and just trying to blend the data before they can even get to insights. And once they get to these insights, it's very hard to scale these insights across the entire organization. So what is the solution? What makes Petro.ai very unique, and how do we address the problems? So Petro.ai really eliminates this analytics friction across the entire organization by providing you, the operator, a digital workspace where you can now work with all of your data across the entire asset. So what makes us unique is that we do three things that no other application provider can do. So we give you, the engineer, the ability to analyze all of your data. This is your operational and subsurface data through one lens, and that's over 100 data types today and growing. We also give the ability to work with our growing application libraries so that you now can learn and collaborate across the entire asset with all your peer disciplines. And then you can operationalize those insights and inform the strategy of the entire business. This combination allows for an increased decision confidence with better context. Over the past few years, many of the operators that we've worked with have allowed us to help them solve a variety of use cases, which include A&D, reserve calculations, completion optimization, drilling optimization, and even focusing on data paths, or what we've also been called science paths. So the value here of Petro.ai is we allow you to expedite your workflows with faster insights and fewer clicks. And with that, I'll turn it over to Kyle LaMotta so he can talk to us more about the impact of well orientation.
Hi guys, we're figuring out we have minor technical difficulties over here. We'll get Kyle talking and then we'll get back to you all shortly and have him restart. Sorry about that.
Anthony, can you hear me now?
Yeah, we can hear you, Kyle. Let me make you the presenter again. Oh, I can't see you though. You're presenting, all right, okay. Sounds like we're good to go. Kyle, if you want to restart and share your screen whenever you're ready.
Okay, can you hear me now?
Yes, sir, we can hear you.
Excellent. Okay, well, I got a good practice on the first couple of slides, so let me jump back in and share my screen again.
All right, awesome, thanks, man. Appreciate it.
Yeah, sorry about that. Okay, let's try this again. Okay, so if I start advancing the slides, Anthony, just jump into the chat and I'll pay attention to that. Okay, so what I was saying was, today I'm going to talk about the impact of well orientation as it relates to production, and then we'll wrap it up with an economic evaluation of what those actual impacts are from a bottom line standpoint. So this is a fun study because it can be done with data that everyone has access to. Really, we're just looking at public production data, well survey information, and general well locations. So what's the motivation behind the study? Well, about a year and a half ago, Dr. Mark Zobak, who is a professor of geomechanics at Stanford University, joined our technical advisory board. And we were really excited to have Mark join the team because as we're developing more advanced applications and thinking about things like completions and stacked pay and optimizing well spacing, we realized that we needed to understand the geomechanics side of things a lot better. So Mark joined our team, and since then he's done several presentations. We've had a lot of fun collaborating with him on the different workflows, and just really enjoyed having his contribution to our team. So today we'll spend some time talking about the stress orientations in different areas. We'll be focusing on the Midland Basin, Delaware Basin, and then also look at some examples of the Gulf Coast Basin and the Williston Basin as well. So what we're looking at here is a map of the stress orientations. The black lines representing SHmax, and then the colored background represents the faulting regime. So the faulting regimes are shaded going from normal to reverse faulting. And in this area that we've kind of zoomed in on in the Permian, it's mostly normal to sort of strike slip faulting. And those are just differentiated by which stress becomes the greatest stress. So in a normal faulting environment, the overburden, or the SV, is the max stress, and the least principal stress is SHmin, which is perpendicular to these black lines that we're showing here. Strike slip, we flip the SHmax and SV, and then reverse faulting, the overburden actually becomes the least stress. So in this example, the study that we're going through, we're going to be looking mostly at normal strike slip faulting. So the kind of the purpose of this is to figure out, does well orientation matter? And I think we all know that it does matter, but there's a lot of considerations here. And when you look at a map, wells tend to be drilled in all sorts of directions. So if this is a screenshot of the Delaware Basin, and we can see the well sticks going from northeast to southwest. They're more north-south, and then kind of the opposite, and everything in between. There's obviously a lot of things to consider when you're placing these wells. There's land grid restrictions, there's physical restrictions, there's just certain places you can't drill wells and place these laterally. And of course, we want to maximize the acreage. You know, we're making an investment in the land, and we want to make sure that we utilize that land most economically and in a way that maximizes the available area. But what we also know is that when we frack these wells, those fractures will tend to take the path of least resistance, which is going to break the rock open in the direction of the least principal stress. So that becomes perpendicular to SH3, which in these faulting regimes that we're talking about is going to be perpendicular to SHmax. So in order to break it open, it's going to propagate in the direction of SHmax. And where those fracks are being oriented are going to affect things like your geometries, the length that the fracks can extend, the amount of proppant placed, and the list kind of goes on from there. So if we think about three different ways that we can drill wells, the blue line is representing the wellbore, and the shorter blue lines that are perpendicular to that are the orientation of the different stages. So we're saying that as you complete the well, these fracks are going to propagate in the direction of SHmax, which is perpendicular to SHmin. So if we drill the wells perpendicular to SHmax, then the fracks will propagate in that same direction. But as the wells start to become oriented away from that 90-degree angle and become more oblique, the fracks tend to still propagate in the same direction, but the angles start to become pretty extreme. And then when you get parallel, you can see that that just becomes even more exaggerated. So the way that the fracks are propagating doesn't change with respect to the way the well is drilled. It's really driven by the stress in the earth in that area. And this has been proven and shown with many different studies. This is an example of a case study in the Duvernay in Canada, where we've got two wells. One well is drilled north-south, and then another well on the same pad is drilled perpendicular to the SHmax line, which we can see with the green arrows. And the dots on the map represent the microseismic events that were created and captured. So you can see the direction that those are going are perfectly in line with that SHmax direction. So they're going to propagate in that same direction, regardless of whether the well was drilled north-south or on a different orientation. Okay, so that's kind of the background. Now I'm going to talk about how we prepared the data and the data that we're using in this study. So for this study, we decided to choose 4 basins. These are the most active regions right now. So we're looking at the Midland Basin, Delaware Basin, Gulf Coast or Eagle Ford, and then the Williston Basin. So we filtered down to wells that were completed within the last 10 years or so, focusing on horizontal wells. And then the metric that we're going to be looking at is 12-month cum oil normalized per foot. So after we take our public data set and narrow it down, we end up with about 40 to 43,000 wells. So the next step was preparing this data. So we brought in these 3 different data sources. We were focusing on well header, monthly production, and well surveys. And we brought this into Petro.ai as a way to organize it and a way to give us a digital workspace to do some of this analysis. From there, the horizontal sections were extracted from the wellbore surveys. We wanted to use the surveys instead of just the well sticks coming from the surface and bottom hole locations to give us a better representation of the actual well orientation. So we pulled out the horizontals based on an inclination angle, and then used the heel and toe locations to establish the well orientation. So we can look at some of those examples in a minute. And then from the production data, we calculated the 12-month production from each well, and then normalized that per lateral foot from our wellbore survey extractions. So on the right, we see a distribution of that 12-month accumulated per foot, colored by the different basins. The next step was to figure out what the well orientation was relative to the stress orientation for each one of these wells. So what we're looking at here is some stress orientation locations and orientations. This is the data that we showed previously that Dr. Zobak has collected with a number of other people. So the black lines on the map represent the stress orientations, and we use that along with our well locations and interpolated each stress orientation onto each well location. So in order to compare the well orientation angle with the stress orientation, we wanted to get a stress orientation measurement on every single well. So we did an inverse distance weighting interpolation to take the sparse data from the stress orientations onto the wells. So after we did that, what we end up with is for every well location, you can see the horizontals represented with those purple lines, and then those gray lines are showing the SHmax direction for each one of those wells. Okay, so I mentioned we brought data in, and then the data coming out was the interpolated stress orientations, the cumulative productions, the heel and toe locations for every well, and then the lateral lengths. Okay, so the next step was to calculate the orientation for each well. So at this point in the study, we've got our production metrics, we've got our well locations, we've got our heel and toe locations, and we've got the stress orientation for every well, but we haven't calculated the orientation of each well yet. So the way that we did that was just using those heel and toe locations, taking a calculation of how many degrees from north-south each one of these wells was. So when we plot these all on top of each other, what this is showing is each well bore normalized at the same XY coordinate. So basically just stacking them all on top of each other and then splitting it out by county. So this lets us look at some interesting trends where the Delaware Basin, it looks like most of these wells are either north-south or east-west, where in Reeves County and Ward County and Loving County, you get some that are more oriented northeast to southwest. Midland Basin, most of the wells are north-south. There's some wells here and there that are oriented a little bit off that, but just looking at the density and where most of those wells are falling, we can see that there's a lot of north-south orientations. Gulf Coast, which is the Eagle Ford, it's kind of all over the place, but a general trend of northwest to southeast. And then Williston Basin, we see sort of the same thing in McKenzie and Mountrail County, but in the others, most of these wells are either north, south, or east-west. So on the right, we can actually see a distribution of the orientation degrees from 0 to 180 for each one of these basins. So in general, most of these tend to fall closer to 180, but there's still quite a bit of scatter in the data. So next, we'll look at the stress orientation, the interpolations that we did for each well location. The blue lines are the locations of the stress orientation that I showed earlier, and then the gray lines are the interpolated values. So like I mentioned, we did the IDW interpolation, and stuck that on every well. And I just show these charts to give you guys confidence in the interpolation method, even though the points, you know, there's some pretty rapid changes in areas like the Western Delaware Basin, but just getting a general trend, we can see that the interpolated values follow very closely to the measured blue values. So Williston Basin, not as much data, same thing in Gulf Coast Basin, but the stress orientation is pretty consistent in those regions. So if we plot our well locations next to the stress orientations for each well, here's an example of Delaware and Midland Basin. So we can start to see the relative well orientation with respect to the SHmax. Okay, so thinking back to one of our first slides where we talked about how the fracs are going to propagate in the direction of SHmax. So ideally the wells would be drilled perpendicular to that. The next step was to take the difference between these two orientation angles. So in this chart, we're showing the well orientation minus the SHmax orientation. And we've got a measurement from 0 to 90 degrees for each one of these basins. So for every well, we've got a calculation of its orientation with respect to SHmax. And then we can classify those, just for the sake of grouping them, into 3 different buckets, whether they're parallel, oblique, or perpendicular. So just to clarify here, a well that's perpendicular would be oriented perfectly, you know, it would be drilled perfectly perpendicular to SHmax. And then a well that was parallel would be drilled in the same direction as SHmax. So on our diagram at the bottom, the black line is SHmax. The blue lines are the well, representing the wells, and then these angles are just showing us what we're categorizing into perpendicular, oblique, or parallel. So we're grouping anything within 15 degrees of SHmax perpendicular, anything within 15 degrees of parallel, we're calling that parallel, and then oblique is everything in between. So we can look at this a couple different ways. On the histogram, you get a sense of whether wells are more perpendicular or more oblique, and we can see that it's sort of bimodal, where there's a pretty large group of wells that are perpendicular to SHmax, but then there's a large percentage that are more oblique. And then if we color them on the map, we can see spatially where these different classifications are for each well. So now that we've calculated the well orientation, we've got the stress orientations for each well, we can start to try to pull out relationships of production to see if the wells that are drilled perpendicular to SHmax perform better than those that are not. The first step we can do is just plot this with respect to our 12-month cum oil for each one of these basins. So what we're showing is for each basin, we've got the 3 different bars for each one of those orientation angles. And then the red lines are representing well counts. So the first one on the left, the Delaware Basin, there's about 174 wells that are parallel, about 5,000 that are oblique, and then a couple thousand that are perpendicular. But we can see on the y-axis for the blue bars, the 12-month cum oil, we're looking at the median value for this group, is increasing as the wells become more perpendicular. And then the Midland Basin, not a lot of variation, very similar numbers in terms of the 12-month cum oil, but really small well count for wells that are parallel, where oblique and perpendicular have the majority of the wells. And then for the other 2 basins, we can see similar trends of increasing well count and increasing 12-month cum oil as the wells become more perpendicular. So it's an interesting observation, but the real question is, can we show statistically that these groups are different? And then can we actually classify or quantify the economic impact of that difference? So the way that we decided to test for that is using an ANOVA method. ANOVA is a really good statistical test for different groups that have large populations. So what we're doing is it's basically splitting our population per basin into different bins. And so for Delaware Basin, and for all these wells, we've split them into 15-degree bends, where again, 90 is perpendicular, 0 is parallel to SHmax, and then we can look at the different relationships of these bends. So what ANOVA does in a pairwise comparison is compares every group to every other group. So in our case, we've got these different bends of 0 to 15, 15 to 30, 30 to 45, 45 to 60, and so on. So we end up with 6 different bends for each one of these wells, or for each one of these basins. And we can compare each one of those to all of the others. So if we, and don't worry, we'll provide these slides so you can kind of dig into this later. But if we look at this first row, we're looking at the comparison of group that's within 30 to 45 degrees to group 2, which is 75 to 90 degrees. And what we're looking for is p-values that are less than 0.05, which is going to show that there's a statistical significance between it. So it's picking up that there's something different about these two groups, and then giving us a confidence interval around that. So we can cut this off where the p-values are greater than about 0.05, which is showing us that each one of these individual pairings is statistically different from each other. And then on the right side, we can see the different well counts in each one of those. So we've got pretty decent well count in each one of these bends. So if we were to draw a line here, cutting off our relationship after this p-value hits 0.05, we're seeing that most of these are different from one another, which means that we can start to kind of dig into that and see what the difference is in terms of how much more production we can attribute to being drilled in a more optimal orientation. So this is the Delaware Basin. We can see, oops, yeah, so there's that line. We can also see the Midland Basin. Not as much difference here. So this one's interesting because they're all relatively similar. There was no statistical difference really between the different groups, which we saw that as well on the production response. All of those groups had about the same amount of 12-month cumul. And then Gulf Coast Basin, similar results to Delaware Basin, where each one of these groups is different from one another. And same thing for Williston Basin. Not a lot of difference in some of these oblique to oblique comparisons, but in general, the ones that are more parallel to more oblique, we're seeing pretty large differences. So if I come back to this slide, this is what we were showing earlier with the production comparison. We can start to quantify the percent difference. So for oblique to perpendicular in the Delaware Basin, parallel to oblique, we get a 33% increase in 12-month cumul per foot, and then about an 18% increase from oblique to perpendicular. Midland Basin, there really wasn't any statistical difference. So we can calculate the difference, which is about 19%, but it's hard to say whether that was caused by the orientation or if there's something else going on there. And then Gulf Coast West, so a really big jump from parallel to oblique in terms of performance, not quite as much from oblique to perpendicular, and the Williston Basin, kind of the same story. So what we're seeing for most of these basins, there's just getting the wells off of parallel, making them more oblique, and as you trend towards perpendicular, really big performance improvement just to keep them from being parallel. But then there's still pretty significant gains to be had from going from oblique to perpendicular. So the challenge here, though, is that as you start to change the orientation of the wells, it starts to affect how the wells can be placed within your different lease blocks and might not maximize the acreage as well. So the real question is, okay, so it's great that there's an 18% increase from oblique to perpendicular, but if we orient our wells so that they're perfectly perpendicular, can we actually have an economic number of wells based on what we're investing in this pad? So that was the next step, was to look at a type curve analysis. So we're gonna compare two different scenarios where we're optimizing on well orientation, and another scenario where we're optimizing on acreage maximization. Okay, so here's our first scenario. We're going to think about 4 sections, and we're going to think about how we can place the wells in these sections. So I think traditional method would be, let's think about our well spacing, how far apart should we space our wells, and then how can we place them evenly to take up as much space as we can on our available lease. So in this case, we've got 4 sections that are about a mile each, and if we space them about 700 feet apart or so, we can fit 12 wells in here. So each one of these wells is 9,000 feet. They're spaced evenly. So for this area, we've got 12 wells maximizing this acreage. Our other scenario is if we orient these wells so that they're more perpendicular with respect to SHmax, we can't fit as many wells in the lease just because of the way that they're oriented. You know, we can't change the land grid, but we can change the number of wells that we're placing in our acreage. So in this case, we can only fit 8 wells if we keep everything the same. So we kept the well spacing the same, we kept the lateral length the same, but just rotated them a bit without having one of these wells go beyond our lease area. Okay, so here's our 2 scenarios, 12 wells versus 8 wells. And I'll come back to this slide just to remind everyone that even though this is basically representing what we're showing here, you've got a vertical, or you've got these horizontal wells that are oriented either north-south or oriented perpendicular to SHmax. Either way, the fracs are going to propagate in the direction of SHmax. So for our first scenario, we've got the 12 wells. If we fit a representative type curve, so we took the wells in the Delaware Basin, and for these wells, we found that representative type curve had initial production of about 900 barrels, 1.2 B factor, 70% initial decline rate, and a terminal decline rate of 0.06% or 0.06. So that gave us a 12-month cum oil of 173,000 barrels with an EUR of 712,000. And if we look at the other scenario with 8 wells, we've got a very similar type curve, but we increased our 12-month cum oil to account for the fact that these wells are going to be more productive based on what we saw through our ANOVA analysis. So the increase in production we're assigning is 13%, and that gives us a 12-month cum oil of 196,000 barrels with an EUR of about 807,000 barrels. So the way that we did this was make these 2 type curves basically shift up the curve, kept everything the same in terms of the well orientation. What changed was the well orientation, the well count, and then the oil QI. But what we did was just bumped up the curve, kept the same type curve with a more productive version with a higher 12-month cum oil. So if we look at these 2, not a lot has changed. We changed the orientation, we changed the well count, and we changed the initial production to account for the productivity increase from being more optimally oriented. So if we compare these 2, our 12-month cum oil is 196 versus 193. So the ones that were oriented more optimally had higher production, but we've got fewer wells overall. So the question is, are these going to be economic? So just to wrap up, what didn't change was the well spacing. We kept the well spacing the same. The lateral length stayed the same. Our parameters and our type curve stayed the same in terms of the B factor and the decline rates. The timing stayed the same. So this is a pretty big assumption where we assume that all of these wells were drilled and they came on and started producing at the same time. So when we go into our economic analysis, we're saying that all of these wells started at the same time. Which, if we're drilling a 12-well pad, maybe there's 2 rigs going, maybe there's 1 rig going. But in any case, the pad with more wells, that cash flow is just going to be delayed. So the present value of it's going to be lower in the case where you're drilling more wells. But in this case, just to simplify things, we kept the timing the same for both. And then the economic assumptions that we'll look at in a minute, they were the same for both pads. So really, we just wanted to focus on the change in well orientation and the associated economics. Okay, so now we'll look at our economic analysis of these two different scenarios. So our 12 wells, we got the 900 barrel per day type curve, and we're going to assign a total CapEx per well of $9 million. So multiply that by 12 wells, our total investment is $108 million. And if we run the economics on this at $50 oil, which is, when I made this presentation several months ago, seemed like a reasonable number. We got an NPV 10 per well of about $4 million with a total NPV of $48 million. Now, after, a month ago or 2 months ago, we changed this to $35 oil, but since then, obviously things have changed pretty significantly again. So we'll kind of dig into that in a minute. But if we'd run this at $35 oil, this well in this pad is no longer economic. So you're sort of breaking even on one well, but those small losses add up when you multiply by 12 wells. But if we think about optimizing for orientation, so fewer wells, but more productive wells, same CapEx, but we only have 8 wells this time, so the total investment is $72 million. At $50 oil, these wells make about $6 million each for a total NPV of $47.5 million. But the interesting thing is at $35 oil, just that small uplift in productivity makes these wells economic by about $1 million with a total NPV of about $8 million. And so that's, let me summarize the economics real quick, and then I'll show one more slide. So if we put these side by side, we've got our acreage optimization and our orientation optimization. So well count 12 versus 8. So we're drilling fewer wells. Our initial production goes up by about 13%. The EUR goes up by the same. The CapEx, so the total initial investment goes down by 33%. And then the NPV per well, it's actually lower per well, but overall at $50 oil, it's lower per well. But at a lower price, at $35, the NPV is much higher. So in lower price environment, this optimization in terms of orientation is significantly improved. And then if we look at payouts, $50 oil pays out about 2.5 times faster, but as we optimize for orientation on lower price environments, we see that payout difference is even better. So this kind of got us thinking, in one case, it's when the oil price is at $50, it seems like, it might not make sense to optimize on orientation. The NPV, the total NPV difference is about the same, so you're getting about the same return for your investment. But when the price drops, the NPV difference is significantly high. So the next step was to run multiple sensitivities, to run this across several different price scenarios, going from $10 to $80. And it's kind of interesting that this crossover point is right around $50 a barrel. So what this is showing us is these two different type curves, if we consider one versus the other and run economics on all of them, as price starts to increase, optimizing on something like orientation is not as important, but as the price starts to drop, then it really does become even more important, and the difference becomes quite significant. But even if we were to see where this breaks even, so our better type curve, this gray line, which is our 807,000 barrel EUR type curve, that's still only breaking even at around $30 oil. So even if we optimize them on orientation and we place 8 wells with these different type curves, we're still only breaking even at around $30 in this scenario. So the question is, how do we shift this curve? How do we make it affordable, or how do we make it economic at $20 oil or $10 oil? So taking our same analysis, but thinking about how do we move this curve to the left so that we can still be productive in a lower price environment. And so that's sort of beyond the scope of this talk, but there's some interesting things that we can think about, like what are some further optimization steps that we can take? So we can think about the stress state and the frac gradients. So looking at vertical frac gradients, looking at vertical stress profiles, and how not only does well spacing matter in terms of horizontally, but also vertically when we're completing in stacked pay environments like the Midland and Delaware basins. You know, how different is well spacing in different areas? How important is it to think about well spacing on a pad level versus just an overall field level, both vertically and horizontally? What are the depletion effects, parent-child relationships, things like that? How does well placement and patterns come into play? Should we place these wells in a wine rack view, or should we think about each well more individually? How can we think about the patterning and the well placement on a more specific well level? And then think about things like area of stimulated fractures. So as we're creating fractures, how much area is contacted in the reservoir, and how do we think that connects back to the well? And then frac geometry. So as we're completing the wells, where do they go? How do we start to think about the frac geometry and the effect on production? So that's sort of how that's how we take it to the next level, I think, is you know, well orientation is certainly important. We see pretty big productivity gains, but it's not the end of the story. There's lots of things that in this type of environment that it's a good opportunity to slow down and think about it and really dig into some of the further optimization steps. So a few key takeaways, and then we can open it up for questions. When you think about well orientation, I think a lot of times we think about it just how is the well oriented? Is it north-south? Is it east-west? Is it somewhere in between? But it should really be considered with respect to the stress orientations, SHmax and SHmin, because that's really going to dictate the direction that these fracs propagate. And I think an interesting thing to do would be to start thinking about well orientation during type curve analysis. Most of the time, as we make type curves, we think about, okay, what basin are we in? Which bench are we landing in? How long are our laterals? So we might come up with our Wolfcamp B 7,500 foot type curve. But maybe we break that into two type curves where we've got Wolfcamp B 7,500 foot optimal, you know, oriented 15 degrees with SHmax, and then another one oriented within 30 degrees of SHmax, and look at those type curves in that way. Just by optimizing on something that is sometimes simple, not always simple, but as simple as orienting the well a little bit differently, we can see pretty significant production improvements. So certainly going from more oblique, getting off of the parallel, but as it becomes even more perpendicular, we can see that those productivity gains are just accelerated. So there are significant production improvements, and even economic ones at that when you can think about how the wells are oriented and also maximizing the land available. So that kind of brings us to our last point. If possible, think about optimizing on orientation and some of these other factors we talked about when possible. And of course, obviously the price environment is very important when you start planning these things out. So that concludes the talk. I hope you found this beneficial. I'm happy to answer any questions at this point.
Hey, Kyle, this is Ronnie. I will be handling the Q&A for you guys. If you would please raise your hand if you'd like to be unmuted to ask a question audio. Otherwise, you're also welcome to go ahead and type your questions in. I'll try to keep them organized, and we'll kind of go back and forth between the written questions and the audio questions and allow Kyle to answer all those. Okay, so we are now open up to questions. The first one has come in from, let's see, Sumia Ahmed. It says, oh, just lost that question. Where'd it go? Sorry about that. How was the interpolate SHmax values calculated?
How are the SHmax values calculated, or how are they interpolated on the wells?
I'm not sure. It says how was the interpolated SHmax values calculated? I'm not sure. Ahmad,
okay.
Sorry, Ahmed, did you want to clarify your question?
Let me jump back to it.
Okay.
So we have just go all the way home. So we've got the well locations, and then we've got the stress locations from people like Dr. Zobak. Okay, so this is what I wanted to go to. So Dr. Zobak and some others have collected these orientations, these SHmax orientations. And so they do that by a number of different methods, but a lot of times earthquakes and other seismic events will help them determine and calculate the SHmax orientation. So this is a publicly available data set. So we take that, and you can see that there's the black lines are not, there's not as many black lines as well locations. So if we look at the well locations, we wanted to get the SHmax on every well location. And we did that with an inverse distance weighted algorithm using R. So inside of R, it's a IDW, or inverse distance weighted, is a pretty standard interpolation method. And we just interpolated the stress locations and orientations onto the well locations. Does that make sense?
Okay, so Mia, I've gone ahead and unmuted you. Does that make sense to the question? Was that the question you were asking?
Yes, I was. And I do have another question.
Sure.
So you were talking about looking at frac geometries, well length, these as being the next step in your in understanding, productivity. Are you going to be looking into that, and if so, how are you going to go about doing that? And what are you going to first, try to, figure out?
Yeah, great question. So we've started working on a few different projects with Dr. Zobak related to that exact topic. So the way we think about it is in terms of a pad analysis or a tank model. So we'll look at a multi-well pad that has a rich data set around it. So operators will have things, obviously the wellbore surveys, but they'll collect data types like microseismic. They'll have all of their formation tops identified and gridded out, either from seismic interpretation or from tops picking. So we'll understand exactly where the wells are with respect to the formations they're in. We'll know the location of all the stages, the completion stages, and then we have all of the frac data, so the high frequency frac man data. We'll bring that together. And then we've got the productivity of the wells. So there's a number of different data types that we're bringing together. And then we start to analyze it as a pad or as a tank because these things are happening in 3D space. So we'll look at first classifying what is our stress profile for this area. How do we think that the fracs are going to propagate both horizontally and vertically? So from the frac data, we can start to characterize the vertical stress orientation or the vertical stress profile by picking and pulling out ISIPs, the initial shut-in pressures from the curves. And then of course we've got the regional stress orientations. So we can start to understand what's going on in the pad. And then from something like microseismic, we can start to interpret where these fracs might be stimulating. So we can start to see, what area is created as we complete the well. Can we correlate that area back to productivity? And can we start to understand, different frac geometries or different correlations between the job sizes or the type of proppant used or the fluid used or the treatment pressures. So really, it kind of comes down to bringing all these different parameters together, building a multivariate tank model, and trying to run predictions and run calculations, correlations, thinking about it in terms of like a pad or a tank. So it's a really interesting problem, and I think it does take very careful consideration, and then it is well by well in some cases. Like we've seen even in the Midland Basin from a few wells within a few miles, different changes in vertical stress profiles, which is going to affect whether you're containing the fracs in zone or whether they're going to go out of zone and maybe stimulate an area that you weren't expecting. So yeah, that's kind of the approach that we take.
Okay, great. Thank you. I do have one more question.
Sure.
So are you going to be able to utilize the seismic data with maybe, looking at discontinuity models to kind of capture that intensity of fractures by chance?
From seismic or microseismic?
From seismic. Usually you want to incorporate the two, right? To kind of see how the two,
Yep. Yeah, so seismic, typically we won't work with like the bulk seismic volumes, but we can work with attributes that are being calculated onto the well. So I'm pulling out attributes at different points along the wellbore, and then seeing how those parameters are correlating with other ones, like productivity or like stimulated area or something like that.
Okay, cool. Thank you.
Sure.
All right, thanks. So the next question comes from Yoshi, and it is on slide 36. What's the price of gas on slide 36?
Oh, I like slide numbers. That's really helpful. Let's see here. Okay. So our assumptions, I'm going to skip past 36. So here's all the assumptions. We did 50 cents for gas. So we kept it the same for both.
Okay, great. So next is Brian McDowell. He has his hand raised for a question.
Okay.
Brian, go ahead.
Hey, I just had a quick question. So you were saying in the Midland Basin, you don't have much of an effect of the wellbore orientation relative to SHmax. And I was wondering if you took the difference between SHmax and SHmin into account, because, that kind of that difference between SHmax and that wellbore, I would assume had a bigger effect when you have bigger differences.
That's correct. Yep. So let me switch to this one. Whoops. Okay. Yeah, so this area, Midland Basin, is definitely a little bit different. So we didn't check the difference between them, but I think that there might be something else going on. So I do agree that as those two values become more similar, they can start to affect the direction that your fracs are propagating. If there's a really large difference between SHmax and SHmin, then it's going to certainly follow SHmax. But as they start to get closer together, that effect is not going to be quite as strong. So I think that's what you're saying. But I think that in Midland Basin, just sort of anecdotally, what we've seen is that there's a lot more. It tends to be driven more by the productivity tends to come more from connecting existing fractures and not so much relying on propped fractures. So when we're thinking about the orientation and placing proppant, then the prop fractures become very important in terms of the productivity. But in Midland Basin, perhaps that's not as important. Maybe there's a larger network of existing natural fractures that it's more important to connect those back to the wellbore instead of trying to create new fractures and connect those to the wellbore. So that's sort of just anecdotally what I think might be happening, but definitely agree with your point that the difference between SHmax and SHmin is important when considering this.
And I'm curious too, as well as for the Delaware, your pore pressures get so high down there. I mean, your your vertical stresses are almost equal to your SHmax in some areas, correct? Y'all taking that into account either?
Yep. Yeah. So definitely, when you're thinking about let's say your ISIPs and classifying the vertical frac gradient, and considering the pore pressure and overburden, that window does become pretty small in some areas. And that's why I mentioned, this is definitely a well by well, or even like a smaller region by region. To really dig into it requires looking at individual wells and individual pump curves. But yeah, I agree. The pore pressure and those vertical stress profiles tend to vary quite a bit in these different areas.
Okay, cool. Appreciate it.
Yeah, you bet.
All right, thanks, Brian. Okay, we have a couple of questions from Leo Perella. The first one is, what are the key differences between Petro.ai and Drilling Info or Enverus?
Okay. Jared, I don't know if you want to jump in and answer that, or I can take it, either one.
There you go, Jared. You should be good to go.
Yeah, thank you. Yeah, Kyle, I can answer at high level. So we're a data science platform across the entire asset from drilling or from geo to drilling to completions and then to the entire reservoir. And so our goal really is to provide the entire asset team the right tools to make faster and better decisions with less risk. And so in terms of detailed specifics, that's something I would defer to Kyle, but that's also something we'd be happy to take offline and discuss in a further conversation if it makes sense.
I would say one key difference. I don't know, am I muted? Can you hear me?
No, we can hear you. We can hear
Okay, cool. Yeah, one key difference is we deploy our tools inside of our client's environment. So you're not connecting to Petro.ai, more of we're installing Petro.ai and giving you access to these tools. So we're not a data provider, we're a tools and software provider. And we connect your data, both public and private, and all this diagnostic data into Petro.ai so that your team can run these different workflows and connect all these different data sources together.
Okay, thank you. Awesome. Another question from Leo. A lot has been done in the space of parent to children well spacing. What are your views for, say, Delaware Basin?
My views are that's very important. Maybe can you get a little more specific on like what do I think the spacing should be, or what do I think in general?
Dale, did you want to speak on that? I'm not sure. I've tried to unmute him, and it looks like he said spacing should be. I'm not sure where he's going from there.
Okay, well, I think in general, obviously well spacing is very important, but there's a lot of factors that are tied to well spacing. So maybe in one area, or let's say one well, you've got really high intensity fracs for a pad. You might see a lot of interference between two wells that are next to each other, let's say 500 feet apart, whereas another pad you might have less intense fractures that you're not seeing that interference just because you've changed the completion design. So, you know, well spacing is certainly a factor of your completion design and job sizes and things like that. But there's also, you know, stress considerations like we talked about here. I think that vertical spacing is not talked about as much as it should be because, you know, the stress is changing vertically as well, and that's going to dictate how wells propagate or how the fracs propagate. Certainly the lithology is important. Maybe certain stages shouldn't be completed because they went through a clay-rich zone. Maybe the stages shouldn't be evenly spaced, or maybe we shouldn't have the same cluster design on every stage and the same stage spacing for every well. So in general, my thoughts are, you know, if we're focused on optimization, especially in a lower price environment, we should really think about it at as granular level as possible as we're, you know, making these really large investments in each one of these well pads. So I guess my thoughts are, you know, it's case by case, and it's even well by well and stage by stage in terms of how spacing can affect the performance.
Okay, great. Next question. I'm sorry. Does that answer your question, Leo? I believe it does, yeah. Okay. Next question from Jeff Hudson. Did you break out the spatial component? Looks like some of the data was geographically isolated.
Let's see. So what do you mean by geographically isolated?
Jeff, I've unmuted you. Did you want to be a little more specific on your question? Okay, I'm not sure. Maybe we can come back to that one. and see. Let's see. We'll go on to the next one, and then maybe we can come back to that if you want to type something a little more clear.
Okay, that sounds good.
Let's see. The next one comes from Robert Walker. It says, how do you account for acreage coverage limits in your economic comparison of orientation differences? You may lose lateral length due to lease limits in a certain direction. Therefore, may not have the same lateral footage per well, etc.
Yeah, totally agree. This is a very idealized view of 4 sections that are right next to each other. If we, cut the box off the top right, then, it definitely changes the picture. So I was trying to just think about how we can simplify this and eliminate as many variables as possible and just focus on the impact of just a small production uplift. So really, I mean, this production uplift could come from orientation, it could come from a number of different factors, but we're just saying we've got 2 different scenarios. We're changing one small thing about the second scenario, which is the well count and the productivity, and then seeing what that economic impact looks like. So yeah, I totally agree. This is idealized. It's it's again case by case when you're actually putting these wells and planning out the locations of them. Does that answer the question?
Yes, apparently so. He said thanks.
Okay. Cool.
The next one, going back to Jeff, he did send a clarification. He said some of the azimuth bends were in parts of the basin and not in others.
Okay, let's see. So are you saying like these blue lines are in some parts but not others? The SHmax orientations?
He's saying slide 21.
Slide 21, okay. So is it like these gaps here that we don't have wells? Is that what you mean? Kind of in Delaware, I don't know if you can see my cursor, but northern part of Delaware and then the eastern, southeast, southwest Williston area. Is that what you're referring to?
Sorry, waiting on a written response. Similar to Midland, all blue is in the south.
Oh, yeah, I mean, that's just, it is kind of what it is. We didn't, when we're doing the ANOVA study, we're just comparing the orientation with respect to SHmax. So we're not considering spatial considerations. We're just isolating that one variable of perpendicular, oblique, and parallel. And so each one of these wells, we've got a difference, and we're just plotting them here. So yeah, the map is interesting because you can kind of see where these groups are. These are more oblique in Midland Basin, but that would be a good thing to include in a multivariate study where you've got, this is one input, so the well orientation with respect to SHmax is one of your variables, but then the other variables would be like the formation that you're in, the lateral length, and then the spatial components like you're saying. So I hope that, I'm not sure if that answers the question, but the point of the map chart is to show visually or spatially where these different groupings are.
Okay, I've got a couple of comments from along that line. One from Sumia again. Northern part of Delaware is because of the salt potash area. And then Jeff comes back in and says the poorer wells in Midland are in the south.
Okay, that's interesting. Yeah, and I mean, you guys have very intimate knowledge of these areas, and that's why, it's really important to have, we're not relying on the machine to tell us the answer. We like to work with people that really understand these areas, so that all of those insights are really valuable.
Okay, I have a question from Madi Adad. You showed in one of the first few slides microseismic data from Dr. Zobak's GeoMac class, north-south well versus northwest-southeast well. Hydraulic fractures can grow in length differently if the wells are drilled at different orientations. Did you assume different hydraulic fracture lengths will change with change of well orientation at later slides for economic analysis?
No, so the difference here is actually this vertical, the north-south well, was completed with slick water, and then the other one was completed with like a gel frac. So, and I might have those mixed up. So one is slick water and one is a gel frac. So that's the difference in the extent. So that this one's, you know, they're changing two variables, they're changing the orientation and they're changing their fluid used. But you can see that they still propagate in the same direction. So no, we didn't consider a difference in like frac length or anything.
Okay, any other final questions, anyone? Okay, well, thank you guys for the question and answer version of this. Brittany, would you like to come in and have a few final words?
Yeah, thanks again, Kyle, and thanks again to Petro.ai for sponsoring and presenting. Thanks to everyone who joined us today. We'll be hosting another event next month. As I mentioned earlier, please follow us on LinkedIn for more details on that event. And I hope everyone has a great day.